You play an important part in CSXT's fuel story. Hi, I'm Carl Taylor, Senior Vice President, Transportation and Mechanical, and Chief Transportation Officer. We all need to be aware of the opportunities we have each day to conserve fuel and help keep our environment clean. A group of our co-workers has already come up with best practices for locomotive fuel handling techniques. Their recommendations will enable us to fuel and move road, yard, and local locomotives in a more efficient manner. As a team, we can make a difference in the amount of fuel we use each and every day. I challenge you to practice the techniques you've seen in this video. Techniques like throttle modulation, dynamic braking, and shutting down unneeded engine units. As a high-performance organization, we all need to be aware of the roles we can each play in fuel conservation. It's a team effort. Management supports these best practices, and I challenge you to do your part in helping CSXT be an industry leader in fuel efficiency.
The business of CSXT is running trains. Trains pulled by locomotives that burn diesel fuel. At any one time, we have 2,500 to 2,700 locomotives burning fuel. That's a lot of fuel going up in smoke, and it's certainly one of our biggest operating expenses. Some of that fuel gets burned needlessly, wasted. But that doesn't need to happen, and you can help. There are many ways to conserve fuel and prevent waste without affecting the quality of service we provide customers. If you're an engineer, dispatcher, or yardmaster, you need to know these fuel-saving techniques, and maybe you already do. If so, bear with us. For the next few minutes, we're going to review ways that you can help save fuel. Why should you want to conserve fuel? Take a deep breath. The air that we breathe is affected by exhaust from internal combustion engines. That affects you, your children, and someday your children's children. As individuals and as a corporation, we all need to be pro-environment. As I said before, fuel cost is a big part of our overhead, and that's another reason to conserve. To stay competitive with other forms of transportation, we've got to cut waste and keep pricing low. And that's how CSXT will retain customers and be financially strong for you. How much fuel can you save? Well, that'll vary depending upon how much conservation you're already doing. So we're proposing a modest goal. The average locomotive consist carries about 10,000 gallons. Our fuel-saving goal for every road crew is a tiny fraction of that amount, just 50 gallons a trip, less than 1% of your total payload. Now, for yard crews, the goal is just 10 gallons a day, about a tenth of 1%. If every road crew and yard crew can meet these fuel conservation goals, it would amount to free fuel for every locomotive on the railroad for an entire month. And that's something we're shooting for. In the early days, it was pretty easy to monitor fuel consumption. Engineers on the old coal-burning steam locomotives could literally watch the amount of fuel that they used. This was the fuel injection system back then, a simple matter of opening the door and shoveling. And the concern over air pollution was not nearly as much as it is today. Today, this modern diesel fuel injector is invisible to the engineer. Perhaps the reason we overuse fuel is because it's out of sight, out of mind. We use a tremendous amount of fuel going nowhere, just idling. Older locomotives use as much as 5 gallons per hour idling. A Dash 8 uses 3.4 gallons per hour at regular idle and 2.7 at low idle. To show how this adds up, take a consist of 3-8s. At idle, they'll consume 1 barrel of fuel every 5 hours. Idling 4 or 5 hours a day, the consists can waste over 300 barrels of fuel a year. If 200 consists, like this one, idled for the same 5 hours every day for a year, they'd use up over 2.5 million gallons of fuel, not to mention the considerable amount of exhaust fumes put into the air. We have over 2,700 active locomotives, so these figures are not far-fetched. An excellent way to prevent this waste is by using the lowest possible idle speed. Most locomotives automatically do this for you. However, you can make doubly sure by making a habit of centering the reverser lever whenever you're sitting at idle. Even better than low idle is shutting down units when they're not in use. This sticker is in many cabs to remind you to shut down those engines whenever time and conditions permit. And the sound of saving fuel is the sound of silence. Every day there are opportunities to save fuel by shutting down engines here in the yard, and your train handling rules provide good reminders. They state that units should be shut down during lunch periods or any time they're not in use, whether in the yard or in helper service. This, of course, when the temperature is above 40 degrees. In the yard, there's no minimum time required to be stopped before shutting down. Another situation is after you've yarded your train, shut down all but the controlling unit. And when you arrive at the locomotive facility, shut down the controlling unit, unless shop personnel are there and ready to take over. At the end of your tour of duty or when you're being relieved on line of road is another opportunity to shut down units, unless of course your relief is right there. When light units are being moved, you can shut down the ones not needed for movement. And anytime units are set off on the line of road, shut them down. Here in the tower, the yardmaster can do his part.
CSX Yardmaster Waycross calling CSX engine 5573, over.
CSX engine 5573, over.
5573 going to be blocked for about a half an hour while R68405 doubles out. I thought you'd want to know, over.
Appreciate the information. We'll shut them down until you can let us go, over.
CSX Yardmaster Waycross out.
By communicating delay periods to engineers and crews, the yardmaster can help them know when it's okay to shut down without hindering workflow. Out here on the line of road, the rules are slightly different, but the idea is the same. Shut down the units that you don't need. An engineer should constantly ask what is the least number of units needed for this run. During your trip, if you set off cars, you may be able to go on to your destination with fewer locomotives running. And of course, anytime you're going to be stopped and waiting for longer than 30 minutes, shut down all but your lead unit. This is also referred to specifically in your train handling rules. Here in the dispatching center is another place where conscientious action can prevent waste. A dispatcher can relay critical information to road crews about the places and the length of time that they'll be stopped, information that allows them to take the best fuel-saving actions available.
This is CSX AS Train Dispatcher Jacksonville calling CSX Train N14205, over.
This is CSX N14205 to the AS Dispatcher, over.
Putting you in the siding at Smithville to meet 3 eastbound trains, over.
Okay. How long do you figure, over?
I say you'll be stopped 1.5 hours maximum, and the first train won't be there for 40 minutes, over.
Message received. Thank you, over.
CSX AS Dispatcher Jacksonville out.
Well, Jimmy, we got this stop coming up in Smithville. What do you say we just ease off and coast in?
Well, ain't no sense in rushing to wait.
Yeah, why waste the fuel? We'll just take it easy for a while and we won't have to wait as long when we get there.
When the crew learned they had a stop coming, they were able to use the information and decided to throttle down and gradually slow the train as they approached the stopping point. The fuel savings can be substantial. Then, knowing they were going to wait an hour, they shut down their 2 trailing units. By using throttle modulation, the crew saved plenty of fuel. This chart shows the fuel consumption at the different throttle positions, going from position 8 to position 6. The savings can be as much as 60 gallons an hour. You may have a sticker like this one to remind you to use throttle modulation to adjust your speed instead of braking. Now, speaking of brakes, Many engineers still feel that they need to rev up their engines to maintain main reservoir pressure. On a Dash 8 and many other locomotives, this is no longer necessary. The electric motor driving the compressor is independent of the main diesel engine and will run at twice diesel engine speed when the throttle is in idle or the number 1 position. On older locomotives, you may need to rev up to pressurize the system. However, there should be no need to use higher than throttle position 5 to maintain a 15-pound differential between main reservoir and brake pipe pressure. When it comes time to put on the brakes, the technique of stretch braking or power braking can use up fuel needlessly, especially when other braking methods will work just as well and use much less fuel. Stretch braking or applying heavy brake pressure at full power is like adding several extra cars to your train, cars that don't pay their way. The better method is to reduce your throttle and use the throttle modulation method for speed control. Just look at the fuel savings in a consist of 3 Dash 8s. Reducing throttle from number 8 position to number 6 can mean a savings of over 191 gallons per hour. Dynamic braking is another effective alternative to power braking. In fact, according to your train handling rules, if you have operative dynamic brakes, 1 unit on a single unit consist or 2 units on a multiple unit consist, the stretch braking method will not be used for speed control. By reducing throttle and applying the dynamic brake, it's possible to reduce speed at a significant savings over stretch braking. These figures show a potential 74% fuel savings. Another important factor in fuel conservation is the operating condition of equipment. A locomotive that needs maintenance not only wastes fuel, it puts unburned exhaust gases into the air, creating pollution. You can do your part by observing engine exhaust and reporting smoke that indicates a poorly running engine and unburned fuel. Look for a steady stream of white smoke, a steady stream of dark smoke, white puffs of smoke or dark puffs of smoke in the exhaust, or a spray of oil. Note them on your locomotive work report. Tell the yardmaster if in yard service, train dispatcher if in road service. With your sharp eyes, good train handling techniques, and the cooperation of our dispatchers, yardmasters, and maintenance forces, we can have the most efficient running trains in the country, and the reduction in emissions will help us all breathe easier. Remember that good train handling and fuel conservation go hand in hand. The techniques that we've shown you are all part of the professional skills that CSXT employees take pride in. By making them part of your everyday operating style, you'll help us reach that important fuel-saving goal of 50 gallons a trip on the line of road, 10 gallons a day in the yard. So take to heart the things we've talked about, like using the engine low idle system and shutting units down at every reasonable opportunity, using the minimum number of units on the road, using throttle modulation instead of heavy braking to slow or control your speed, maintaining the main reservoir pressure using a minimum of engine revving, or none at all in some cases. We talked about the fuel-saving advantages of dynamic braking over stretch braking, and finally, the importance of monitoring and reporting diesel engine performance. All of these techniques are consistent with good train management, but more important, they're consistent with our environment and consistent with running a lean, efficient railroad that's going full speed with a clear signal into the 90s. Track train dynamics is a term used to describe the forces between the coupled railed vehicles of a train and the forces resulting from the train interacting with the track. The study of track train dynamics is not new. Derailments and damage to equipment and lading have been around since the earliest days of the railroad industry. More recently, research into train track dynamics has been conducted under a joint industry-government project at the Transportation Test Center near Pueblo, Colorado. Here, on a special 4.8-mile test track, trains run day and night. In this manner, the equivalent of 10 years of wear and tear under normal conditions can be accumulated in a little more than 1 year. In the test center lab, technicians place locomotives and freight cars on a test bed and subject them to the same conditions encountered in train operations. The test bed shakes, rattles, and rolls the equipment to the point of breaking. Much of what we've learned about track train dynamics from the tests performed at Pueblo have been applied to operations at CSX. This program will summarize some of what has been learned about track train dynamics and how proper train handling can reduce in-train forces. As an engineer, it is up to you to control those forces, but to do so, you must have a proper understanding of the forces involved and how they develop in train operation. These forces must be controlled, or damage may result to locomotives, cars, our customers' lading, or the track. Now, let's take a look at some of the forces produced by a moving train. To portray these forces, we will utilize the Advanced Display Monitor from CSX's TDA simulators. This simulator graphically displays several elements of in-train forces. Draft force, displayed above the zero force line, is the tension that exists between the couplers when a train is stretched, as with starting. It is caused by tractive effort and also occurs when pulling a train up an ascending grade or from any stretched slack condition. Tractive effort is the force exerted by a locomotive on the track to get a train moving and to keep it moving. Tractive effort is measured in pounds or kilopounds. The key thing to remember is that tractive effort decreases as speed increases in a given throttle position. Buff forces are displayed below the zero force line and are measured the same as draft forces. Buff force is a compression force that exists between couplers when the train is bunched. Buff forces are created by a run-in of slack, backup movements, or from the retarding forces developed in dynamic braking or from the train air brake application. Retarding forces developed through the use of